Hey, big shout out to Kate, our tech wizard for the night. Good job. It's figuring, but I should off that up. Yeah, thanks, Kate, for hosting us tonight, and thank you to the Yukon Science Institute for inviting us up here. We're kind of in a unique position for this talk because over the last week, we've had a crew of researchers up for a development grant workshop that we've been kind of working on and applying for the last year. So it's really just by chance that we have this crew of research scientists conducting research in the Yukon that are here to present tonight. So yeah, really thankful to all of them for bringing their time up here to kind of work with us and advance projects that further the state of groundwater knowledge in the Yukon. I'm getting there. I'm getting there. Yeah. Yeah, so my name is Cole. I'm the Yukon Government Senior Groundwater Scientist. I've been in this role just for a portion of this year, backfilling for my predecessor, who was kind of the initiator for a lot of these projects. But I've been fortunate enough to kind of carry things on for him and work with that same research team I was talking about earlier. But there's been these projects, all of them have been multiple years in the making, and I'm just kind of cutting in at the midway point and kind of getting them across the finish line here. Okay, so here's some of the topics we're going to talk about today. So I'll start with giving us kind of an overview of groundwater in the Yukon. I'm sure there's varying degrees of familiarity with this topic in the room, so we'll keep things kind of high level, keep it more or less brief, and then get into kind of the more technical part of the presentation, which will be a summary of 3 research projects going on in the Yukon. So the first project, we're kind of going from like a broad Yukon scale to a more local Whitehorse scale. The first project will be presented by Jeffrey McKenzie, who's going to present about a project assessing the hydrogeology of the Southern Lakes region, including Whitehorse. That has kind of started since the big flooding year we had in 2020. So that big event is sort of the focus of this research, and just understanding how groundwater affects kind of surface hydrology processes in Whitehorse and the Southern Lakes. I'll pop back up for a little bit to talk about Yukon Government's aquifer mapping programs, which we've been doing for the last 4 or 5 years, culminating this year in mapping of the Whitehorse aquifer systems, which is by far the most complex and most involved endeavor, just because of the density of data we have in this area. Going to like an even more local scale, we'll invite Elliott Skierszkan up to present on the AGWA project, or assessing groundwater in the Whitehorse area, which is a project involving a huge research team and just characterizing the groundwater quality around Whitehorse. Yeah, kind of going from like a large Yukon scale down to like a more specific. Okay, so I'll start us off with a quick introduction of groundwater in the Yukon. So not many people know this, but Yukon's actually the second most groundwater dependent jurisdiction in Canada, second only to PEI. An impressive 97% of Yukoners rely on groundwater for their drinking water. So of that 97%, about 2/3 of the Yukon are in the Whitehorse area, and all of Whitehorse relies on a single aquifer system that we'll get to in a couple minutes. We have very few people in the Yukon relative to our kind of geographic coverage, and as a result of our small population base, groundwater resources in the Yukon are not as well understood as they can be. So in regions like Ontario and Quebec, where you have just like hundreds of thousands of wells spread throughout the province or territory, they have a lot of really dense data, whereas in the Yukon, we're really concentrated just around Whitehorse and a few small municipalities. So kind of the theme of all these studies is like working around a real scarcity of data. Jeff and Elliott will talk to this a little bit, but groundwater is really essential to the Yukon's water cycle and to the hydrogeologic regime. So the processes that we think of as controlling flooding, like snowmelt and rainfall, those are very intimately connected with groundwater recharge and discharge systems. So we'll get into how those things kind of interplay together later in the presentation. Okay, so focusing on Whitehorse a little bit for kind of the groundwater backstory. So there's 6 wells in Whitehorse that serve almost the entire population of the Greater Whitehorse Area. And those wells are all located in what we call the Selkirk Aquifer System, which is in the back of Riverdale here. So the blue lines on this chart here show the water mains in Whitehorse. There's almost 190 kilometers of water mains, all from those 6 wells in the Riverdale system. So if I can zoom out a little bit here. So this is an image showing that same water distribution network, but with private domestic water wells spaced throughout the rest of the map. So all those red dots represent wells that aren't a part of a municipal drinking water system. So a really important characterization here is, or difference, is that the Whitehorse drinking water system is rigorously tested every week or every couple of days. And it's a regulated municipal drinking water system and is subject to really stringent testing protocols. But the private domestic wells spread throughout Whitehorse aren't actually subject to any kind of mandatory testing. So it's up to private well owners to get their own well water tested. And we've really been encouraging that as part of these research projects, is if you're on a private well, you need to get it tested and take those results to someone who can help design treatment systems. Okay, so I'll give a brief overview of just kind of the field we're talking about tonight, which is hydrogeology, or the study of groundwater. So as I mentioned earlier, groundwater is kind of an underappreciated part of the water cycle in Canada, and especially the Yukon. So groundwater can contribute to surface runoff events like flooding. It provides the vast majority of the flow during the river months, where there's no kind of surface water melting and recharging those surface water bodies. Anytime you see a stream flowing, or basically any water flowing kind of January onwards, that water source is from groundwater. So it's a lot more intimately connected with surface water than people think it is. And one of the challenges for researchers in this field is that a lot of people just don't really know the importance of groundwater and how it kind of plays into their daily lives. Okay, so this is kind of a complicated diagram here, but we'll work through it from the bottom up to show you what are the typical components of a system that holds groundwater, and how can these components be of use to us as municipal residents or as private domestic well owners. So starting from the bottom, a common thing throughout Canada and the world is almost everything sits on bedrock, or just a hard rock that underlies everything that sits on top. So bedrock is generally fractured to some degree or another. Some bedrock has very little fractures, some is reduced to almost rubble. But in these fractures, you'll frequently find water if you go down deep enough, and that's what we really call groundwater. Is water that fills the spaces between cracks or between kind of coarser grains as we get higher up into the diagram. A lot of people think of groundwater as like kind of a cave system underground with like underground rivers coursing through it, but unfortunately, it's a little more boring than that, which also makes kind of garnering public interest in this topic tricky. Groundwater is really just water that fills the spaces between other materials. So as we move upward through the diagram here, you can see we've got a layer of low permeability till. Can you raise your hand if you know what I mean when I say till? Any guesses? Yeah, most people. Most Yukoners are pretty familiar with kind of glacial geology, which is us. So till is just any material that has varying sizes of grains in it. And a lot of the time, till tends to contain a lot of fine particles like clays and silts. And those fine particles will restrict the movement of groundwater up and down through a system like this. So if you have a really thick till layer, like there's a really thick layer of that in Shallow Bay, which separates two aquifer systems, it's really going to restrict how much groundwater can come from up down or from down up. So at the top of our diagram, also very common and widespread throughout Whitehorse and the Yukon, we have what we refer to as overburden. So overburden is just anything that's not bedrock or like really fine materials. So it consists generally of kind of gravels, cobbles, sands, some silts, but it's a lot coarser material. And if you pick it up, you can kind of like crumble it away in your hands. So if you look at the clay cliffs, we would call that overburden. If you ever like been on the Yukon River, you can just grab overburden from the top and kind of crumble it in your hands. The key difference between these three units is how easily water can move through them. So till layers in the top area, water tends to move a lot more quickly through them. And in bedrock and shallower or deeper systems, water can be a lot more tightly held and harder to get. So you can see we've got kind of half this diagram in blue and half in gray. So anywhere we have water filling the spaces between particles, so whether that's unconsolidated overburden material or fractured bedrock, anywhere we have water filling the spaces between particles, we refer to that as kind of obviously the saturated zone. And everything above that area we refer to as the unsaturated zone, where the spaces aren't filled with water. The interface between those two zones is a really critical concept in groundwater science, and it'll play into some of the talks we have later tonight. But that interface between the two zones we refer to as the water table. Can any of you raise your hand if you've installed a well or been a part of a well installation before, either on your property or otherwise? Yeah, lots of people have. Whitehorse has a pretty strong country res population, so the concept of a water table is really critical for installing your own well, because obviously if you install it in the overburden, in the unsaturated zone, you're not going to get any water. If you install it in the saturated zone, you're more likely to get water. So drilling wells is always a bit of a trade-off. You want your well to be as shallow as possible because drilling wells is insanely expensive. I know this firsthand from drilling my own country residential well a couple of years ago. So drilling wells are really expensive. You want to keep them as shallow as possible, but you want to get them deep enough that you can pump usable quantities of water from your well. So if you drill a really shallow well in the overburden, kind of at the top of the saturated zone, that area, due to its high conductivity, we call it, or the ease that fluids can move through that layer. If you drill a really shallow well up there, that well can be more vulnerable to infiltrating contamination from the surface, be it a tank of diesel that you've got for your assorted motorized toys in the backyard, or so shallow wells can have a higher risk of contamination. But as you get deeper through into bedrock, drilling becomes a lot more expensive as you drill into hard rock. And those waters in bedrock will have had a lot more time to kind of sit there and interact with the native minerals to that bedrock. So that's not to say you can't get good water from deeper wells, but the pumping rates can be a lot lower in bedrock, and those waters can become a bit more mineralized. So that's when you get kind of the harder, like calcium, magnesium, iron rich, and kind of other things that Elliott will talk about tonight on the scale of the Whitehorse area. So installing wells is always a trade-off, and really expensive, and it's no fun for anybody except the drillers, in my opinion. Okay, so moving forward to a project that I am kind of running these days is the Yukon Observation Well Network. So this network was kicked off in 2001 with a single well located at the playground in the Wolf Creek Country Res neighborhood, which is where I currently live. So I see that well on a daily basis, and I'm always reminded of history from whence you came. So since that one well in 2001, we've grown to include 87 wells spread throughout the territory. You can see this map is from last year. So we have wells in pretty much every major center, if you can call them centers, and quite a few kind of in the areas between along highways and landfills. A key characteristic of this network is that all of our wells are background wells. So even our wells that we have installed in landfills, they're located in places that are designed to be unaffected by any kind of human-caused influence. So it's a really useful network for just knowing what is the background quality and quantity of groundwater across the Yukon. So a quick sell and spiel for Jan here. So we have 87 wells as of 2025. So at each well, we monitor the groundwater level every hour. We monitor the temperature of the water, and we monitor the conductivity of that water, all on an hourly basis. So all of the data from all of our network wells are available online. And certain wells, we started to install systems that broadcast data to our online servers every 4 hours. So if you live in Mayo or near Army Beach, Carmax, and shortly 4 other locations that we're installing this year, you'll actually be able to go and look at groundwater levels in your own backyard, updated every 4 hours, which is a really cool thing that we're stoked to be implementing in the next couple of years. We do kind of a bunch of other more niche scientific activities. Like we measure the properties of the aquifers, so how fast water can move through those aquifers. We do temperature depth profiling for like geothermal purposes. Yeah, all this to say, we have a lot of data generated by this network, and just not a lot of time and power to invest into analyzing these data. So that's why we've really been focused on building partnerships with assorted academic groups to help us analyze these data and produce something useful for Yukoners from this awesome wealth of data that we've accumulated from the network. Yeah, so yeah, we're always looking for more research partners. So if any of you know any researchers who are interested in this kind of stuff, we really encourage everybody to kind of reach out to their networks and let us know if they have any kind of capacity they can provide or assistance they can provide for analyzing our data. So speaking of research partners, I'll pass it along to our second speaker of the night, Jeffrey McKenzie.
All right. Thank you, Cole. That was a great introduction. So I'm Jeff McKenzie. I'm a professor of earth sciences at McGill University in Montreal. And yeah, obviously I'm here. I'm talking about hydrogeology. My specialty is hydrogeology. And I really work on, I sort of came up with the, I like inventing words. So I invented the word cryohydrogeology. So we really focus on groundwater in cold places is what I like to study. Yeah, for a brief moment, I thought I should get like projects in Hawaii or in the tropics, and it just sort of never panned out. I keep on just going to cold places. All right, so I have a project. I'm going to give you a little highlights of what we're going to do. It's just starting this summer. And just tell you a little bit what we're working on, and then Elliott will talk more about the Whitehorse work that he's doing around water quality. And so the project we have is also with another colleague, Dave Rudolph, who is not here today, who's at the University of Waterloo. Second. So just a little bit of research motivation. So as the north warms, groundwater intensity increases. So I invented this term groundwater intensity. It's not really a measurable idea, but this is an idea that as we go through climate change, groundwater can potentially become more mobile. We have things like permafrost, frozen ground can start thawing. So we have more liquid ground in the subsurface, and winter starts to change. Right, we might have shorter winters or more snow. We just have more intensity of the hydrologic cycle, which then can start changing groundwater systems. And so we think about northern places, there's a few different ways that this idea of groundwater intensity can be manifested. There's just more potential for groundwater to move through the subsurface. Right, so maybe we have less freezing in the winter, right? So we have warmer winters, so there's more potential for groundwater to move through the subsurface. A big question in the north, maybe not as much around Whitehorse, but as we start moving farther north, or especially into the eastern Arctic with the peatlands, a lot of carbon stored. So this carbon now can start to become more mobile and transported by groundwater through the subsurface, in addition to rivers and streams. Higher potential for contaminant transport. So the north has more contaminated sites per person than southern Canada has. So this is a very serious concern. More groundwater resource development. So the Yukon, I think, is really ahead of the curve in terms of using groundwater as drinking water source, with 97% of Yukoners using groundwater for the drinking water. And also just more infrastructure degradation by groundwater potentially as well. We'll get to this in a second, one way that this might happen. These are some of the research motivations that I think about. But then I also think there's some very real concerns for Northerners as well. Right, so obviously Yukon, 97% Yukoners using groundwater. About half of Alaskans use groundwater as a drinking water source. And then if we look at the other two territories, Northwest Territories and Nunavut, there's really almost no groundwater usage, except for a couple of communities really in Northwest Territories. But still, we're very concerned about the groundwater, both from drinking water standards and contamination of groundwater. Once groundwater is contaminated, it's very difficult to remediate this contamination. And there's also some real potential to use groundwater more as a drinking water source, potentially, where it's not being used right now. So one of the things that we did, myself and Brendan, I wanted to say Cole, but this is before Cole was in his current job, and also Stephanie, who's here, we had this idea of Under the Land, where we went over a couple of summers and we visited a bunch of communities across NWT and the Yukon and just talked to people, and in particular to a lot of different First Nations, about groundwater. So oftentimes people visit a community and we go on the land and we visit and we talk about what environmental issues. We want to go under the land. And so this idea of making the invisible visible, we talk to communities about groundwater. And so we learned a lot. And broadly, so I think if I had to generalize things that we learned over these couple of summers where we did this, one, the communities are concerned about groundwater quality. So people want to make sure that the water they're drinking is clean and safe for themselves and for their families. And the impacts of climate change on the management of water, and with subsequent sort of knock-on effects to the environment that uses groundwater. So these were sort of the things that we learned out of this, and we decided from this that we really wanted to do more research on this topic. And the area where we ended up focusing on is the Southern Lakes. So this project was just funded sort of the end of last year and really got going. And this summer, we're just kicking off the field work. So I don't have any like immediate results. We'll give you some results, but sort of give you an idea of what we're going to do with this project. So the Southern Lakes, I feel like I'm embarrassed telling people here what the Southern Lakes are, but this is the chain of large lakes that all feed down and form the headwaters of the Yukon River. And a few of the, to highlight the big lakes that people talk about, Marsh Lake, Taggart Lake, and Bennett Lake are sort of the best. Not the best. There's the whole this set of really large lakes. Culturally and ecologically significant, especially for First Nations communities that live in these areas. And the Southern Lakes are in the news a little bit right now as they provide the flows that are eventually used. We go through Marsh Lake, which is controlled, the level of Marsh Lake is controlled during the winter, and then it eventually goes down to the hydroelectric plant that's here in Whitehorse. So this is a really critical area for numerous reasons, economically, socially, and for water resources. So the project now, we've been calling it Beaches. Brendan and I like coming up with fancy names. So this took us forever. Bennett and Army Cryohydrogeological Environmental Study. It's a mouthful, but Beaches sounds cool. So we've been using this term a lot here, the Beaches Project. And it's a project that's been funded by NSERC, so the National Science and Engineering Research Council in Canada. And it has some partners, the Yukon Government, also Yukon Energy is very interested in this research. So we're working together to try to better understand groundwater in the Southern Lakes region. And just briefly, sort of the objectives of this project to give you a sense of what we're going to do over the upcoming 3 years. When we're just trying to understand how does groundwater, this water that's stored in the ground, how does it end up in the Southern Lakes? So groundwater can slowly move through the subsurface, right? We know this, we see springs sometimes, right? Or we see, streams, say, flowing in the winter time. This water is coming from groundwater that's eventually making it to the surface. So we better understand how much groundwater is making it into the Southern Lakes. That'd be one question. We also want to understand how does climate change then affect groundwater in the Southern Lakes and potentially affect this connection between groundwater and surface water. And we also want to sort of better develop tools that help us understand groundwater in the Southern Lakes. So there are ways we can sort of take the data that we collect to sort of predict a little bit how it might change in the future. So research approach for beaches. We have 2 sites where we're really focusing on a lot of instrumentation to really try to understand process. And then we take what we find from these 2 sites and we try to scale it up and a lot of arm waving to understand what's happening across the Southern Lakes. And the 2 sites are Bennett Beach. So Bennett Beach is just in Carcross and Army Beach is on the shore of Marsh Lake. And we have a bunch of different things we're going to do. Obviously, a lot of data analysis. And I'll show a little bit of that coming from the Young, this Yukon Observation Well Network that Yukon Government runs. Some numerical modeling, which is really my specialty, a little bit of water chemistry, and trying to sort of getting at this idea of how old is the water that's stored in the Southern Lakes, and how old is this water that eventually makes it to the lakes. So how old is the groundwater, and then how old is this groundwater that makes it to the Southern Lakes? So we have a bunch of different things we're going to do. We've also been doing some snow surveys at our 2 sites. And then this summer, in fact, in August, we're going to be back and installing a bunch of sensors to better understand, for the upcoming winter, to better understand how, say, like snow melt recharge. So snow melts, hopefully, right? And the snow melt then eventually goes into the subsurface, and then how this sort of affects and builds up how much groundwater is stored in the subsurface. So this is one of the sort of where this is all going with the project. So again, we've not collected a lot of our own data right now, but we have been spending a lot of time thinking about this observation well network data that Cole and Brendan and a lot of other people have worked really hard on over the past, since 2001. It's crazy to think that's what, 24, 25 years of data collection, sort of put this data together, try to see what we can tease out of this data from the Southern Lakes. And really, it's just been in the past, 5 years that, this first well was installed or instrumented in 2001, but then it was like another 15 or 20 years before anything else was added to the network. And it's been sort of this exponential growth in terms of this observation network in the past, especially 5 years. So it's gone from like 20 wells in 2020 to like 87 at this moment. So there's been an incredible explosion of data, but we're trying to figure out how do we deal with all this data. And so one thing that's worth pointing out is that Yukon is unique. So this is all the sites across northern Canada and Alaska, where there's sort of basically government observation wells. So it's not industry sort of, observing itself. This is where people are actually observing groundwater and are doing continuous groundwater observations. So this is where they say every hour, every day, we know how deep it is from the land surface down to the water table. All right, and what stands out of this really quickly is Yukon is doing a lot. Right, so this is not actually all, this is from a year ago. So this is, I think this is like 70 of the observation wells. Now there's 87 of these sites in the Yukon. I think there's something like 12 in Alaska, there's 13 in Northwest Territories, 3 in Quebec, and that's it. So if you want to sort of go online and get this sort of open access data, Yukon has the data. So Yukon is doing an incredible job, I think, in terms of what we're actually observing right now. And it makes sense too, that we think about everyone using groundwater, we want to understand groundwater. So, and just to give you a sense of this data density, so the USGS, US Geological Survey, for the lower 48 states, they have 8,500 observation wells. So this is still not a lot when we sort of put it into that sort of into that kind of context. And again, so what we can do, we can go in, and this is sort of following up on what Cole showed before. You yourself can go to the you search in Google for Yukon Observation Well Network, Yukon Government. It takes you to the website. You can click on things, and you can eventually come up and you can see what's the depth to groundwater for a location over time. It's really, really cool. So this is available to anyone to download. If it doesn't work, you can just email Cole. That's what I do. Okay, so what have we found out? So I'll just give you a couple of highlights of things we figured out, just really digging into this data. And then I'll let Elliott give a bit more local information. So bottom left here, ignore the rest of the slide, just look on the bottom left. This is this is actually from a textbook about groundwater in Canada. And what this diagram shows here is runoff. So runoff is how much water, this is sort of generalized, obviously. This is what we think happens to rivers. Runoff is the runoff of rivers in Canada, let's say southern Canada, right? So obviously in the spring, snow melts and rivers, have a large flow, and so the flow in rivers increases, and then that slowly drops through the summer, it dries out. Then in the fall, we have storms, we get these sort of tropical depressions that come out through eastern Canada, and then you sort of refill the rivers a little bit, there's a little bit of flooding, and then again this falls, and through the winter flows drop, and then we repeat this cycle every year. And groundwater, so the water table, this is the depth to water, sort of follows a very similar pattern to the surface water, right? So it rises when all the snow melts, we get the snow melt recharge, it rises, and then we get these storms in the fall, and we get sort of a second rise, but not as large as when snow melts, and it sort of follows this sort of dashed line pattern that you see. So when we went through all the Young data, we see something a little bit different. So this was sort of something that we sort of say we need a northern theoretical model. So we sort of proposed up the top there, this is not published yet, but so what we now think is happening, that really everything is dominated by snow melt. Right, so you have all that snow, the snow melts in the Yukon, that all, not all of it, but a lot of it goes into the ground, and it causes groundwater levels to rise. And as groundwater levels rise, that's the single basically event that happens throughout the year. There might be a little blip that happens in the fall due to some storms, some rain events in the fall, but really all we see is snow melt seems to be the single event that controls groundwater in the north. All right. So let's take that sort of idea. So this is sort of interesting in and of itself. So we have sort of a slightly new conceptual model of how this works. And the other thing, and I'll admit this next slide here, this really originally came from Brendan, but then I've thought a lot about it. And again, we love our fancy names for this stuff. So we call this the groundwater staircase. And so this is looking at groundwater levels at the observation well that's in Tagish, near, I believe it's the well that's near the solid waste facility in Tagish. All right, what we see is going from when the well was installed in mid-2019, the summer of 2019, going all the way through to 2024, is that groundwater levels just continue to rise and rise and rise year over year. So this sort of freaked us out a little bit. Like where does it stop? Right, so this is sort of a little bit concerning, but what we actually think is happening is that in the years, so the blue line is where the water table is. We see it going up and up and up. It's higher every winter, it's higher every summer. We get sort of this step feature going up and up. And these arrows I put on here with the numbers So the numbers are how much snow there is. So if we had the snow, if we were to melt it all, how thick would that water be? So 178 millimeters, so that's a lot of snow. And then the percent after it is how that compares to the historical median. All right, so I was not here in the winter in 2021, but there was a lot of snow in 2021. Right, in fact, we were at 153% over the historical median of how much snow there was. And in 2022, we went to 173. In 2023, we went to 156. So we had some really snowy years, excessively snowy years here in the Yukon. And then when the snow melted, it was more basically snow melt recharge than the system could remove. And we had sort of like a net, I don't know, net positive. We just kept on adding more and more groundwater year over year. And so we sort of didn't expect this. We thought that every year things sort of returned to equilibrium. This sort of shows why you need observation wells. We would never have thought of this unless we had the observation wells. So we sort of saw this pattern, and there's a little bit of noise in the data. We always expect a little bit of noise, as you see, but this is for hydrogeology. This is shockingly smooth. This data looks really nice, and this like really clear. This is what's happening. So we had this idea, the groundwater staircase, and it's sort of cool. But it also would make you sort of nervous a little bit, right? So if you were living in, you talk to people in Army Beach, right? A lot of concerns about basements flooding. Right, actually, the term people use called groundwater flooding. So this idea that there's flooding happening, but it's not water coming in your front door, but it's that water is coming in your basement. And that's because the water table is coming so high that it's then intersecting where your basement is. And then all of a sudden you start getting, you're like, oh my God, there's water in my basement. Where's it coming from? And it would be this sort of type of setting would happen. And just anecdotally, I've heard a lot of stories about new springs appearing where there were never springs before during these times, and just groundwater sort of being a place where we didn't think groundwater was going to be before. And so sort of this idea, we think of the staircase has caused some of these problems to happen. And I'm trying to remember, yeah. And so we see this across a whole bunch of different observation wells across the Yukon, right? So it's not just that one location. So we're seeing this sort of pattern, this stepping pattern, especially from 2020 through to 2024 or 2023, happened at a lot of different locations throughout the territory. And right, all of this upward trend, right? So we saw this really sort of mind for me at least. I was like, oh my goodness, this is crazy. This is happening across the entire territory. Now it's even more crazy, I think, too. If we look in Northwest territories, right, where they've had less water, right? The McKenzie River's never been drier, but Yukon right now has this incredible events happening. And we can actually go through and sort of map out where do we find these observation wells that show groundwater flooding. And they're pretty ubiquitous across the territory. So this is sort of this is ones that have sort of the perfect staircase. I only map these up here. So all the up arrows are where we're seeing the staircase happening. Circles are where we don't see the staircase happening. In a couple of spots near Kwach'an Lake, we see groundwater levels have actually dropped. And that's probably a feature of the lake level itself dropping. So Kwach'an Lake has decreased in terms of its water volume. Okay, so this is some of our initial findings on this. I think I'll leave it with this just to say, groundwater, just reiterate what Cole said, groundwater incredibly critical for the Yukon and for the North. Climate change is going to increase potential vulnerability. We're seeing changes in the groundwater system. And for example, this sort of snow pattern, this groundwater staircase, I think I would argue is a little bit climate affected. We're seeing these atmospheric rivers coming up through the Yukon more and more. Right, we're getting more snow. We think this is somewhat related to climate change. And hopefully you'll have me back in a couple of years and I can tell you about what happened to the beaches, give you the update on the findings of this. Yeah, so we're just starting this project now, but I think it's going to be some really interesting and hopefully relevant results will come out of this research. So thank you, and I will bring up, Cole is coming up next, and then Elliott. Thanks. Yeah.
Awesome, thanks, Jeff. So continuing in our theme of kind of grand scale to smaller scale, I'll give you just a very quick 5-minute overview of some aquifer mapping projects we've undertaken in the last couple of years. So the aquifer mapping initiatives that we've completed so far have been in Teslin, Watson Lake, and Carmax. So for those 3 locations, you can go online into our water data visualizer, and you can actually see the outlines of those main aquifers for those municipalities. So these projects have been carried out by a consultant overseen by Yukon Government, just because the amounts of data that are required to ingest for this endeavor is is massive. Like it's every borehole log that we have in our database is taken into account by them and kind of ingested into this 3D modeling software. And they produce these really cool 3D models of aquifers for these communities. So our most current endeavor, kind of to support what Elliott's going to talk about and Jeff's work, is the creation of an aquifer map for Whitehorse, which is, in our opinion, long overdue. Due to the reliance of our city's reliance on groundwater, understanding where our aquifers lie and what geologic units are under our city is really of critical importance for Yukoners. So we're in kind of the preliminary stages of this project so far, but from this image, you can see all these dots that represent boreholes or drill logs that they took and kind of adjusted into this model. So you can see the purpose of those wells listed at the top. Unrelated to the colors of the topography. Sorry, that's a little confusing. But this is just kind of like an initial screenshot of the data they've collected so far and the work that they've kind of begun to assemble into one cohesive model. What's really cool for this project is we've asked them to 3D print us kind of a large model of this aquifer with nice fancy colors. So we'll have like a big base. And we'll be able to kind of like take that aquifer apart unit by unit and see how those different geologic units kind of nest together. Because the average person doesn't like looking at technical diagrams on a screen. It's beyond most people, myself included. So yeah, we're excited to have that visual aid for our next science talk that we'll do hopefully next year if we get invited back. So accompanying that Whitehorse aquifer model, this is sort of the initial foray we took at developing a conceptual model of what's going around for groundwater around Whitehorse. Elliott will get into kind of the structure, the geologic structure of Whitehorse. I won't belabor this too much. But in short, we've got a lot of snow and rain infiltration into the Mount Mac Highlands on that side. We've got a wetland zone kind of near the Copper Hull Road that serves as a discharge feature. So groundwater leaches into those wetlands from below and then also infiltrates from those wetlands back into the ground. So it's a cool zone with lots of areas of upwelling and infiltration. It's a really interesting area that we're hoping to kind of better understand in the coming years. So downstream of those wetlands, we've got Wolf Creek, Cowley Creek, all those kind of country residential neighborhoods that rely on groundwater that's been coming through the subsurface through that area. As we go through the clay cliffs, most of you have probably seen the springs coming out of it or like the landslides that happened on those cliffs. Those were all the results of groundwater welling out of that kind of feature at a contact between that silt below and a less permeable or coarser sand on top. We could do like a whole other presentation on groundwater's impact on those landslides, but for now, just know that groundwater generally flows from the Mount Mac Highlands through kind of those Wolf Creek country res subdivisions, through the clay cliffs and into this Yukon River basin here, which comprises of mostly sands. The Selkirk aquifer system is in those same Yukon River Valley sands. So those wells are at a really interesting interface between kind of groundwater coming from up gradient from both sides and kind of interacting with river water in that area. We want to do a question? Yeah, go ahead.
Yeah, I'm curious, is the pattern similar coming from the other side, from Grey Mount, that we have a similar kind of infiltration, or is it asymmetrical?
Good question. Yeah, so there'd be some degree of infiltration from that side as well. It's just not nearly as well characterized because very few people live kind of in that Grey Mountain area. There's very few wells there. The geologic mapping is really focused on kind of the downtown and like Copper Road area. But there is definitely significant infiltration that happens on that side, but mostly stops at the Yukon River. So it'll have influence on the Selkirk aquifer field, but in terms of any of the kind of the AGWA focus area, up gradient near the copper belt and kind of above those clay cliffs, the impact of infiltration from that back area is a bit less. Does that make sense? Okay, this is a nice photo that took at night. Yeah, so there was some previous work done to characterize Whitehorse aquifers in 2003. So the study was completed just based on a very preliminary assessment of borehole logs. You can see the records they took into account of these black dots here. And for comparison, these are all the wells that are taken into account for our current aquifer mapping project. So we've got a mountain of new data to ingest and analyze. So we're really excited for the results of this project when they come out by like the end of the fiscal year. Okay, so I'll pass it over to Elliott to further talk about Whitehorse groundwater and chemistry and other good things. Here we go.
Okay, it's great to see everyone. Thanks for your attention. And exciting times, obviously, for groundwater studies in the Yukon. So we're learning a lot more about this resource because there's a lot of people that are very interested in it. So I recognize a few faces from last night too. So for those of you who were at our event last night, you're going to hear another recap of our project in Whitehorse. Hearing things twice is great because you usually can understand things better on the second round. And for those of you for whom it's the first time, you'll get an update on our project, which has got the nickname AGWA. And this is again Brendan Mulligan's interest in finding great acronyms. AGWA is a wonderful one. So assessing groundwater in the Greater Whitehorse Area. So I'm just standing here. So I'm sorry, Elliott Skierszkan from Carleton University, to reintroduce myself. But I'm standing here on behalf of a large team of people. So maybe those of you who are involved in AGWA, can you just stand up really quick and the room can see all the people who are working on this? All right. So there's a large team of people. This project is funded by National Research Council Canada and by Health Canada. So the NRC funded this project because they had a call for proposals that basically wanted to fund water-themed related research in the north, by and large, and that served community needs and built community capacity for understanding water. So that's where the federal funding came from. And a bit later into the game, we also got an additional grant from Health Canada. And Health Canada took an interest in this project because Health Canada is the organization that establishes water quality guidelines to advise Canadians on what is safe for consumption. And to do that, they need a lot of data on Canadian water quality. So some of the data that we're collecting here in Whitehorse is also being used by Health Canada to refine and update their guidelines to advise people on potable water. So this is a project that really has implications beyond just Whitehorse, although it really serves Whitehorse's needs. So we have several partners on Kwach'an Council, the City of Whitehorse, the Territorial Government, the University of Saskatchewan, Carleton, Yukon U, and then our funders, NRC and Health Canada. So I'll provide some information on our project here, but first I will just speak to the link between geology and water quality. So I started working on water in the Yukon now 6-7 years ago on a project in the Dawson Range. So here you see the Yukon River up there and the White River, so the area in between. And that project was commissioned by Yukon Government to look at why is there arsenic and uranium in groundwater in this area. There's a lot of mineral exploration, no active mining at the time of any of this work. And so here's some figures from a publication that synthesized some of this data. And the map on the right shows stream water uranium concentrations. And so you can see there are areas where there's higher concentrations and areas there are lower concentrations. And this is all in streams that have not been disturbed by mining or any other local significant human activity. And I'm just showing that to point out that you get variations in that water quality. And one of the big drivers is the geology. So the map on the other side is a geological map of the area. And in this area, we found basically the geology just kind of along the north-south boundary of the Yukon River in that area was more conducive to mobilizing uranium. And so that's why we see some higher concentrations in that area. So the geology is an important factor. And we're talking about uranium and manganese a lot. You've surely heard about it as well, because it is something that we're seeing in Whitehorse, which I'll speak to in a few moments. But I want to provide a bit of context too, because see it in the Dawson Range, different metals. It's something that's common in many places across the country and across the world. And what we're starting to do with this project in Whitehorse is just providing a bit of a regional understanding locally of what is driving those parameters. But other places have been doing this for a much longer period of time and have developed a better understanding. So one example I like to pick on is Nova Scotia. So Nova Scotia's got these risk maps or probability maps. So here's a map of Nova Scotia, and they've identified areas where there's a higher probability that bedrock wells contain higher uranium. And that is basically just a simplified geological map. So they've done this through thousands of well samples that have been collected, and they're producing this information for Nova Scotians, where about 40% of people rely on private water wells for their water supply, and about 1 in 15 wells exceed the limits for uranium. So it's something that happens, all over the place, and the emphasis is to understand if it is there, and if it is there, that there are treatment systems that are very effective at removing some of these parameters. Okay, so we'll do a recap of Whitehorse geology, a quick one. This is a geological map. So we got the Carcross Cutoff down here, the Alaska Highway in red, going out to the junction with the North Klondike Highway. And beneath our feet, there's these different rock types. So there's a big swath of pink there. That is granitic rocks. So if you've seen, I'm sure you've seen some rocks like this in the area, they're quite common. So that's all that pink unit. Older than that, and towards Mount McIntyre, there's these bands of blue and purple. And so these are different sedimentary rocks. They were formed from sediments that were deposited off of an ancient sea. And so we have some limestone, some sandstone, some siltstone. And along that contact, so these granitic rocks basically formed when there was magma that entered into contact with these sedimentary rocks. And there was a transformation between those two rock types that produced a rock called skarn. There's a picture of the skarn up there. You also probably are familiar with some of that kind of teal staining, which is copper. So the copper belt, where there's copper mineralization, basically follows the intersection between those two rock types, and also has produced some copper deposits, which have been mined here historically. Okay, the youngest rock in the area is basalt. So you've all been to Miles Canyon. There's all those neat basalt cliffs. So the Miles Canyon basalt originated from a much younger lava flow towards Golden Horn. So there was lava that flowed and filled the Yukon Valley and formed some basalts. So those are the major rock types that we have underneath our feet. And they're all between roughly 250 million years old to 8 million years. Okay, so many millions of years. And more recently, we've had glaciers and rivers that have deposited some sand, some gravel, and till on top of all of this bedrock. So here's a geological map that Pania Lipovsky from the Geological Survey produced that shows the superficial deposits, so these glacial deposits. And here's the Alaska Highway. We're zoomed in. There's the neighborhood of Wolf Creek, Mount Sema, and Pine Ridge. And you can see there's pink bands of bedrock. There's till and green, and then there's fluvial deposits. So these would be sands and gravels that were deposited by moving water in the area. So all that to say, and I should say, I guess blue dots here are water wells. And to produce these maps, Pania basically looked at every single well log she could find to piece together the information. And all that to say, so we are pulling water out of the ground here to drink, and that water is interacting with these glacial deposits, it's interacting with these different rocks, and the chemistry that results from the water interacting with these different materials produces differences in water quality. So the last thing I'd like to mention is that groundwater chemistry also influences water quality. So on the one hand, there's the bedrock, and on the other hand, the chemistry can influence whether or not things are more or less easily dissolved into water. So this is a schematic from a publication looking at groundwater in California. So in the Central Valley, there's the Sierra Nevada, big granitic mountains, and there's a flat valley in the middle that has sediments that have come off of these mountains and filled in a big basin. And most of us are eating lots of food that's produced in Central Valley. It's a very, very big agricultural area. And you have uranium-bearing particles from these granitic rocks that form the sediments, and we're fertilizing massively the Central Valley. And what do we add in fertilizer? One of the things we add is nitrate. And so there can be a chemical reaction between nitrate, that's that NO3 up top, that can react with the uranium in the minerals and leach it out. Okay, so there's influences of the water chemistry in addition to the geology that mean you may have some metals that are more easily leached, and you may have some that are staying in the mineral phases. So it's quite complex, and our goal simply is to relate all of these things together. We're looking at the geology, we're looking at the water chemistry, and ultimately, why does it matter? It's because of the quality of the water, which results from all of these things. So here's a snapshot of a wide group of people who worked on this, just to give you an idea of the number of people involved. And it's not all of the people. And I'll speak a bit for what we're doing for the project. So we're doing a lot of water sampling, clearly. So we're sampling some private domestic wells. So here's, for example, a wellhead. And what we're doing there is we're trying to collect water that's coming straight out of the ground. So we're looking for water that's representative of the aquifer water. You might have water that goes into your home and passes through treatment and so on. The quality of the water and the chemistry changes because of treatment. And for this project, we're really interested in getting the water untreated, coming right out of the ground. So that's what we're sampling. And we are offering, as a courtesy, a free metals analysis of tap water, whether you have treatment or not, just to provide some information on water quality. We've enhanced the monitoring around the historic Whitehorse copper mine. So there's Lindsay from USask driving in a tool that we can use to pull water out of the ground, just beside some waste rock there. And we worked a lot with local students. So we've had students from Yukon Youth, Kwach'an Council, interns with the Yukon Government, and they've all been part of doing some of the sampling. Emily Perot just right here has sampled how many wells last summer? 147 wells. So they've been working really hard to collect samples. You've heard about the observation well network. So Yukon Government's also supported us with some drilling. And this is some drill core we pulled out of the ground last summer. And here's 6 new wells at each of those 3 points. There's 2 wells at different depths that are around the Whitehorse copper site. So we've drilled new wells in there when we've gone from having about 5 wells around that site to now 11, approximately 11, 12 wells that we can sample. Those wells were completed. And when they were completed, we get these steel monuments to protect them and cast them in concrete. Before the concrete had set, those monuments had been removed and vandalized. So this is what they looked like the following morning. So it's a disappointment because it's a significant public investment to produce wells that we can use to obtain information on groundwater. Fortunately, we were able to recover those wells, so we're still able to use them. But we're sharing this so that people can understand to respect these wells because the purpose that they serve is basically to provide information on water. We also drilled some wells towards Shallow Bay the year prior, and that was in response to Kwach'an Council's desire to have more information on water around Shallow Bay. So we have a pretty comprehensive suite of parameters we're analyzing, over 70 chemical parameters. And without reading all of them in detail, I'll just note we're providing information to well owners that gives information on water quality, coming straight out of the ground again, not the treated water. These analyses cost several hundreds of dollars per sample, which we're able to do because we've had a healthy analytical budget through this project. And we're also producing extra specialized analyses that don't really tell you anything about the potability of the water, but that we're using to inform where did that water come from, perhaps how old is it, and which rocks has that water interacted with.
Artificial sweeteners.
Coca-Cola, Diet Coke. Yeah. So for those of you who've had samples collected, we just got our sweetener data back. We have not reported it yet, but it's going to be coming. And those sweeteners are able to tell us if there is water that is moving from septic fields to the water table. So it's not telling you anything about whether or not there's bacteria, because bacteria tends to not travel as far as the sweeteners. So it's providing us an indication of influence from septic water entering. It doesn't necessarily mean there's bacteria traveling. Okay. And I know that sounds a little bit funny, but at the same time, it's a reminder that we are part of the hydrologic cycle, right? And every bit of water that we take in, we send back into the environment. Yeah, we're not testing for hormones in this project. Yeah. Okay, and then we're also doing rock sampling. So we're trying to integrate the information on the rock geochemistry, and Elliott Skierszkan right there is doing his master's looking at the rocks of the area. So here, this map, let's just say I'm really proud of this map and of the team's efforts because it shows all of the yellow dots, the wells that we've now sampled. And you can see from the Carcross cutoff towards Shallow Bay at the top, we have quite great coverage. Over 200 groundwater samples now analyzed. And then this map shows the distribution of rock samples. So we're looking to kind of get a broad swath of the geology in the area too. So in the next few slides, I'll share some of our observations up to date. And I'll start with the rock, and then we'll look into the water. And so for uranium, which is a parameter of concern here, this is the distribution of uranium in different rock types. And that horizontal line shows your kind of average Earth crust. So it's about 3 parts per million uranium on Earth on average. And the rocks that have a little bit more uranium than that would be the skarn, right? So the skarn is that rock that's along the copper belt, and the granitic rocks. And there's 2 different categories of those rocks that we've listed here. So these rocks have a little bit more uranium than average rocks on Earth. Doesn't mean that uranium necessarily leaks out of the rock, because that also is a factor of the, or dependent on the water chemistry. If we look at manganese distribution, so there's 3 rock types here that tend to have a bit higher manganese than average rocks on Earth. So that would include Miles Canyon basalt. And there's 2 kinds of skarn. So there's skarn that's the calcilicate skarn and the magnetite skarn that both have a little bit higher manganese than typical rocks. Okay, now if you look into water quality, so before introducing results on water quality, I just want to go over what water quality guidelines mean. So these guidelines are developed by Health Canada, and they're intended to provide information on health risk. And Health Canada basically comes up with some estimates of, if you're ingesting water over your lifetime, at what point is there potential adverse health effects from different parameters. And so those guidelines are based on long-term risk. Okay, they're not based on short-term consumption. It's more decades to long-term consumption. And as Cole mentioned, there's no regulatory requirements for private domestic well owners. So these are guidelines that are provided to people, and private well owners are responsible for taking their own decisions for whether or not treatment should be done. And they can also get support from the Yukon Government to get advice on treatment. There's 2 types of guidelines. So health-based guidelines are called maximum acceptable concentrations, MAC. And so this is for health-based considerations. And like, raise your hand if you've got iron in your water. Yeah, because we see a lot of iron. Iron, it's not, we don't like to have it. It's orange, it stains, it's part of the appliances. Iron isn't toxic, so there's no health-based guideline. So there's aesthetic objectives for parameters that are undesirable, but not necessarily associated to a health concern. So by and large, of all the samples we collected and all the parameters we analyzed, most parameters fall within Health Canada's guidelines. Okay, so most of the water is good, most of the parameters are below guidelines. And then there are some that exceed those guidelines. And the ones that we see most often, I'll show the results here. It's uranium, manganese, and arsenic. So manganese, we have 17% of the groundwaters that we've sampled that exceed guidelines for uranium. For manganese, there's 23% that exceed health-based guidelines. Manganese also has a lower threshold for aesthetic objectives, because you can get also staining from manganese, just like you do with iron. And 21% of the samples exceed just the aesthetic or not health-based guideline, whereas a quarter exceed guidelines for from a health-based standpoint. And arsenic is a relatively small amount, so about 9% of samples exceed. So these are the parameters that are more likely to be found in groundwater in the area. Again, if you flip these charts around, 80% of samples don't exceed for uranium, about 76% don't exceed for manganese from a health-based perspective, and 90% don't exceed for arsenic. So most of the time the water is suitable, and then we do find a subset of samples where the levels are higher. And iron, about a third of samples exceed that aesthetic objective. So those are the parameters that we see coming up most often. And in the last little bit of the presentation, I'd like to start looking at relationships with geology and water chemistry, because that's ultimately what we're trying to answer in this project. So these plots show the distribution of manganese here in water, and in water that's pulled from different rock materials or glacial materials in the area. So where we tend to see more manganese includes wells that are in the basalt, in granitic rocks, and in the unconsolidated sediments. And so what we think is happening here is we have a bunch of different materials that are susceptible to mobilizing mobilizing manganese into water. And the chemistry of that water probably has an important influence on whether the manganese is mobile. What we know about manganese, its relationship is often related to the presence or absence of oxygen in water. So that's something we're looking at in our analysis. Whereas uranium, the relationship with geology is a little bit more straightforward. And so the tendency to have higher uranium in water is more associated with water that's in the granitic rocks. Here's a map. These are our manganese data. They're randomized within a bit of uncertainty to protect privacy, but this shows the distribution of manganese levels across the Whitehorse area. And you can see the points that are yellow or orange or red, which have higher levels, and they tend to be scattered basically throughout the throughout the Whitehorse area, and that reflects kind of the variable geological sources and chemical conditions that can mobilize manganese. Whereas for uranium, this map shows the distribution of uranium, and what you can see is all the points that are red or orange, which have higher levels, they tend to be along that red background, which is the granitic rocks. And so we can see the distribution tends to be more in bedrock wells in that geological material, and less so, for example, in the yellow basalt. What you also see with respect to uranium is that we have elevated levels of uranium dispersed throughout the area, and that includes areas that are, for example, far from the copper belt. Now, we've also enhanced our monitoring at the historic Whitehorse copper mine site, and that's where we do see the highest concentrations of uranium in groundwater. So one of the questions then is can we distinguish, uranium that's mobilized from breakdown of the material that's been mined and that's found now in waste rock or in tailings? And the map shows already that we do have a baseline source for uranium mobilization, and we have potential mobilization associated with weathering of mine waste at the historic Whitehorse copper mine site. So one of the things that we've been able to do in this project is also analyze the isotopes of uranium. Because uranium has naturally occurring isotopes. We're not analyzing them because there's any health-based consideration with the isotopes of uranium. The isotopes have one or more difference in the numbers of neutrons, okay, more or less neutrons is how you define a different isotope. And the isotopic composition is related to the weathering of minerals that contain uranium. So this next map shows our uranium isotope results. And so we can tell these purple dots and then all these teal dots around the historic Whitehorse copper mine site. So what we think we're seeing here is we're seeing a way with the isotopes to differentiate uranium is associated with weathering of mine waste, which is accelerated breakdown of the rocks in comparison with uranium that's derived from weathering of the rocks in the other parts of the city. So it's a promising tracer. We're still working through these results, but I think it's a promising tool for understanding uranium mobility in the area. Okay, so I'm going to summarize. And I'm speaking on behalf of myself and Jeff and Cole and everyone who's working on groundwater here, that we've learned a lot about groundwater in Whitehorse. We continue to learn more, and in the Yukon at large. So we're coming a long way. There's a lot of effort, a lot of projects that are aimed at understanding this important resource. With respect to Whitehorse, most parameters are within guideline thresholds. We do see uranium and manganese as the ones that exceed most often. I didn't talk about treated results. We have provided results to people for water coming from their tap. The tap water is usually of much better quality. It's not always the case, and the reason for that is because when you have treatment, you need to select the right treatment for the right parameter. And there's a whole bunch of considerations for coming up with the right treatment system. Yukon Government Environmental Health Services is able to support people to provide guidance. So if you have a parameter that you need to treat, they can provide counsel on what the right treatment system would be. That would be the right person to answer those questions. And also regular testing is important. So the water chemistry can change over time, right? So we've only done kind of a one-off blast of this large area, but if you have parameters that exceed, they might be lower or higher depending on seasonality and all sorts of factors. So it's good to test regularly, as well as test treated water to make sure that your treatment system is performing according to its specs. So I think I will leave it there. It's been a lot of conversation. So thanks everyone for your attention, and I'll put it back to Kate to post some questions.
I'm curious about the age and how you tell age, and what you didn't say anything beyond your testing for.
Yeah, I talked about age, but it's a great question. And age is important because a few reasons. First of all, like Cole mentioned, the deeper you go, more likely you're getting older water. And the older the water, on the one hand, it might not necessarily be as renewable, right? It's very, very old. But on the other hand, it's probably better protected from what's happening at the surface. So we haven't worked through the age date data in enough detail to really present at this point. We do see some things that are fairly interesting. So for example, we've sampled some wells towards Shallow Bay where there's a thick sequence of clay, and clay is not very permeable, so it acts as basically a boundary for infiltration. And then underneath that clay, there's a thick package of sand, and then beneath that there's rock. And there's people who have wells that are quite deep into that sand and that deep bedrock. And we look at the isotopes of water. And so in all of the Whitehorse samples that we see, most of them kind of plot relatively close together. And that tells us that they look like rainfall or snowmelt. And then some of those samples towards Shallow Bay plot kind of off the charts. And so what we think those are probably much older waters. And some of the older waters that you find in Canada can be associated, for example, with deglaciation. So we're talking thousands of years old. So that could be what we're seeing in some of these waters. And we're also analyzing for tritium. So tritium these days, tritium is produced in the atmosphere, and it becomes part of the water molecule and falls as rain. And it's radioactive and it breaks down over time. It's not a health-based consideration. It can be produced by the nuclear energy, by the way, but what we're seeing here is not associated with nuclear energy at all. And it breaks down, and you tend to not see any more tritium in the water after something like 70 years. So we haven't tritium data, we haven't looked it up yet. We do see a lot of waters that we think are kind of, something between 5 and 50 years old. And then we also see a lot of waters that have no tritium. So we know that those ones are older than 70, but is it 100 or 1,000? We can't tell with just those tritium results.
Couple of quick questions regarding subdivisions, like Wolf Creek, for example. What would you consider a shallow well? What depth?
You want to take that, Cole? You're a Wolf Creek resident.
It's hard to quantify what's really like a shallow well. Because like in certain contexts, if you have to go to like 150 feet to get water, and all your neighbors have to drill to 300, then the 150-foot well would be considered a shallow well.
Okay, thanks. One more. You say regular testing should be done. How often would that be?
Yeah, great question. So for wells that are nested, I think 15 meters below ground surface or less, we recommend testing quarterly, so every quarter. For bacteria, yeah. And wells deeper than that, we recommend testing every year. But it's also kind of dependent on what you observe in your water. So if you see like a change in your water, or like in quantity or in flavor, it's always worth just doing a test. And while we're on the subject, it's worth mentioning that our environmental health services branch with Yukon Government on Hospital Road offers free testing for bacteria. So you can take a sample bottle to them, they'll test it for bacteria, and then if you have water quality results from your well, collected from the project or from otherwise, you can do it through commercial labs. You can actually take a printout of your water quality results, including all your metals, to the environmental health services branch, and they'll sit down with you one-on-one and help you design a treatment system that's going to be specific and tailored to your water quality. So lots of resources available for that.
Okay, thank you very much.
Thank you.
Yes, I'd like to ask a question about the Tagish area. In Tagish itself, there are 2 public wells that people can get water from. And then, of course, there's the water itself at Tagish Lake. And I'm wondering if someone has a home there, what type of water treatment do you think would be, or if not necessary, but a water treatment system that would be suitable?
Yeah, so any public system like that will have regular testing. So if there's a public distribution point, like at Army Beach or in Tagish, they'll have regular testing to make sure that the water is of drinking water quality. Does that?
But in addition to that, like an in-house water treatment system, is there something you would recommend? In addition to whatever they check it out to be?
Yeah, so that's totally dependent on your water quality. So like I'm in Wolf Creek, and we have a water softener based on magnesium and iron concentrations that were below the drinking water quality guidelines, but I did a Google search for like the optimal, like tastiest water. And found these concentrations that could be lowered a bit. So we installed a filtration system and a water softener, but it's really dependent on what's in your water. Could very well be that no treatment is required, but you don't know until you test, basically.
So I've been told that there are, of these two public wells where you can get water, one has a higher arsenic content than the other one does, but I don't know how you would handle arsenic, for example.
Yeah, I'm not the expert on treatment systems, but
So, I'm not the expert on treatment, but if I understand, you're serviced from a public supply system at Tagish? Like, okay, so that's a regulated system and that water will be treated to meet guidelines. So perhaps there's arsenic in the untreated water, but after it goes through the government run treatment system, it will be adhering to guidelines.
I see. Thank you.
Hi there, I've been watching Ear Lake for 30 years, and when I came here, it was really high, and it was one lake, and then sometimes it goes down to 3 lakes. But I thought it was being drained from somewhere, and it's all groundwater fed. But it hasn't come up in 20 years, even though we're seeing these increases in groundwater. Do you have an explanation for Ear Lake?
yeah, Ear Lake is like a bit of a continuous subject discussion at the Water Resources Branch, actually. So I'm glad you brought that up. It's a weird anomaly that we've been trying to kind of get a handle on for years. We've had lots of public requests for information about Ear Lake. The short answer is that we don't really know what the controls are on it. We know that it's fed a little bit by deep groundwater, a little bit by shallow water. And we know that in that area, there's a few aquatards, like we referred to in that hydrogeologic diagram, of kind of confining layers that will restrict some surface water infiltration. So we don't know a ton about that area, but we know something strange is going on. And we're hoping to kind of look into that in coming years if we have available resources for us. But yeah, Ear Lake is pretty cool. We're keen on it.
Actually, I've got 2 questions or a comment. One is, does the local geology, or how does the local geology, does it confound, or what does it do to your aging calculations? And the other one, just a comment. I believe Ear Lake is also being fed by the creek that drains McLean Lake.
Yeah, so I'll answer the question about the relation between the geology and the age of water. And the biggest factor there is the permeability of the material. So for example, if you have till, it's not very permeable. If you have clay, it's not very permeable. And the water in there will sit there for a longer period of time. If you have a coarser gravel, then the water will flow faster. If you have rock, so for example, the Miles Canyon basalt is a great aquifer because it produces a lot of water. It's got a lot of fractures. The granitic rock has very low porosity, so less ability to store water. And the only place you really get water out of that granitic rock is where there are fractures. So that points to, yeah, certainly the consideration of the geology is going to be an influence in the age of water. And that's something that we're going to look through in terms of our age tracers. We also did put in a proposal for additional funding to understand water flow paths. So the current project that we're working on in Whitehorse is just really mapping the chemistry, but we can't really relate if water is moving in one direction or another underground. We have Stephanie Wright from Queen's University here, who's an expert in water flow and fractured rock. And so what we're going to do with some of the observation well network data and some additional wells that we hope to drill is look at which direction the water is going and use some methods to quantify how permeable those different materials are. And we're going to focus this work primarily along the copper belts, but we'll have more information to share about the flow paths once we've done more testing.
So it's the permeability and the flow, it's not the chemistry of the local rock that affects your aging.
It can be both. I was just going to add that with you can have higher permeability rock or aquifer material where you have old water, when you don't have a way for new recharge, new water to get down there and flush out the old water. So sometimes that old water might sit there for a very long time and sit there and interact with that rock for a long time. If you put a well in and you start pumping, you can pull a lot of water out of it because the rock itself is permeable, but there's really no way in the groundwater flow system to move that water through. So that's, you might drill into some fractured bedrock and you can pump lots of water out of it. And you find out that your water is actually quite old. It's just because that water hasn't been flushed through that system actively.
I think also, trying to wrap your head around these things, you might try and think of, let's say you have two sponges, right? How does water move through a sponge? Kind of moves through this tortuous path, and a sponge is kind of easy because it's got all of these pores. And if you think one of your sponges is a sponge and the other one is a rock with cracks in it, and now where the water is going, it gets pretty complicated pretty quick.
Are you ready for the next question? You're still thinking?
Oh yeah, I'm not ready for questions. I hope you like my sponge analogy though.
So I have a couple of questions actually. For manganese, what are the health effects?
Okay, yeah, so and I'm not an expert on toxicity. If you look at Health Canada's guidelines, they say that elevated manganese can lead to neurological effects. So that's where the manganese concern comes from.
Can you only tell as to whether there'd be health effects from manganese, from whether you get the aesthetic effects like flecks coming through your tap, or that there are high, high health effects? Can you tell which you have?
Yeah, so are you asking how do you distinguish the aesthetic considerations or the health-based considerations? So there are two thresholds.
Okay.
So there's a lower threshold for manganese, which is 20 micrograms per liter. Thanks, Emily. So Health Canada says above that you can start getting aesthetic, and you would see it like manganese. Often you have black staining. Okay. The health-based level for manganese is 120 micrograms per liter, so it's quite a lot higher. And so those guidelines help you evaluate whether you're in the kind of aesthetic consideration or in a health-based consideration. And again, if you have a well that you sample and it's 125 micrograms per liter, you're pretty close to the limit. Perhaps on a test again, maybe you'll be at 110, maybe you'll be at 80, maybe you'll be at 150, right? So it's the same thing as when you go to a doctor and they do medical tests. So you do screening, you might pick up something, they say, okay, let's do another test and see how it is. And so it's probably good to do a little bit of testing if you're close to the guidelines before spending a huge amount of money on the treatment system. So doing a little bit more testing is kind of what we'd recommend before making a final decision.
Okay.
No, I was just going to say that's a really good plug. We are continuing to sample this summer, and if you're in the room and you haven't had your water sampled, get in touch with us because we'll consider sampling your well.
Okay, I have another question. So I live in Hidden Valley. I haven't been out that way, but it's closer to Shallow Bay. So when I had my well drilled, it went through a clay level, and then beyond that was where I got the water. So you've probably already answered this question, but so what does that make it?
That's generally a good recipe for a groundwater well, because the clay layer tends to prevent water from moving from surface down to where your well has been completed or installed. And so it's generally a really good scenario because the clay kind of protects the water below that surface contamination. Now, the only thing I will say is that that scenario can also mean that some of that deep water doesn't have a lot of oxygen in it. And when you, as Elliott mentioned earlier, when you don't have a lot of oxygen, that's this sort of chemical recipe to get maybe some elevated manganese or maybe a little bit of iron in your water, and maybe you do see that.
Iron.
Yeah, iron. And so that's a really good indication that you do have a deep well. When you have a deep well, that there's not a lot of oxygen down there. that doesn't necessarily mean there's a water quality issue, but you might have staining, and it's still good to get your water tested.
Just the very last question. You probably haven't answered this one, but so I'm in Hidden Valley, which is it's just a very small subdivision. It kind of has a U, and it goes from both ends. You kind of come in, then you go down a dip, then you go up, and then at the top, then you go down again and around. So my understanding is from a neighbor that those dips historically once were the bottom of a riverbed. Does that have any impact on anything? Like it's dry now, right? Yeah.
Yeah, I mean, in terms of the topography of Hidden Valley, you know, the river goes through that area, and I think you're talking about the low areas where the river used to be. So basically, in terms of superficial geology, that's going to be an indication of potentially a different type of sediment that's deposited there. So when we have moving water, we tend to have coarse-grained sediments. When we get further away from the channel, we may have finer-grained sediments. So that's all to say that the shape of your landscape is going to give you clues as to what type of sediment you have. And then that will, when we think about groundwater, define, you know, residence, how long water is held there or how it's transmitted through that material.
And I think this is a great conversation with everyone, especially the well owners who kind of made these observations, because it also goes to emphasize a point I'd like to make, which is there's a lot of variability underground, right? So we might be able to provide information on, you know, which aquifer units are more likely or less likely to have certain parameters like iron or, you know, oxygen and so on. But it's never really possible to make an exact prediction. And, you know, just because your property has something, your neighbor's well might be in a completely different unit. It's very, very complex, and it's hard to, we can provide broad generalizations, but we can never make exact predictions. And at the end of the day, it's really about kind of taking ownership of your own well because it's going to be unique and have its own chemistry.
Thanks for being here. This is a question about the staircase. I understand that this year's snowpack was less than the average, and so if you have compiled the data, are you finding that the water table is going back to, I guess, normal level, or is it still like increasing?
Yeah, this is a good question. My understanding is that this year's snowpack was just about average or slightly above, slightly below. Okay, I heard Wolf Creek was slightly above. Anyways, yeah. But so let's say it was sort of back to normal-ish. But no, this is actually the question, right? We need just one, we need to look at this year's data, but I think that really the thing we want to understand is how long would it take to sort of go back to whatever normal is. Right? I don't think 1 year is going to suddenly drop all the way back. It took like 4 or 5 years to get to where we are now. So sort of the question is how long then does it take to recede back to wherever it started from?
I can add to that. So we are kind of just wrapping up our spring season with the observation well network, and we're in the middle of our data workup for this year. But we do publish a yearly report for all of our wells across the Young network. So we show all of our wells if the maximum and minimum levels were higher or lower than the previous years. We publish how many wells in the network showed their highest ever on record, which in 2022 was most of them, and now it's successively less and less year over year. But so far we're seeing most wells start to come off that groundwater staircase and start to kind of approach that equilibrium value. But really interestingly, there's a couple wells that have gone up that staircase, and in the 2 years since that staircase started to, the surface effects of that staircase started to reduce. We are seeing some kind of regional changes in groundwater storage. So we've gone up that staircase. We're staying in the pet house for the data we have now. That could start to decrease in the coming years, but we do see some wells that show an increased storage maybe over the long term, some that are starting to decrease, and some wells that are even still increasing after that big precipitation event that are very isolated from surface processes and have kind of a longer time before those things influence the groundwater.
I just want to add a comment about the use of the word normal and equilibrium too. Okay, so these observation wells have been around for 5, 10, 20 years at the most. And, you know, we're familiar with things like El Nino, which go on kind of, 7 or 8 year cycles. We've got kind of a warming trend in the last 60 years that is kind of eclipsing what we've seen over the last centuries. But the concept of normal is a really challenging one. We really don't have a lot of information for coming up with normal. And I would argue that normal isn't really a thing. Things are always in flux. And the best thing we can do is just kind of see where we're at on sort of seasonal, interannual, decadal timescales. And we can just observe things and see where we're at relative to other years. But I don't know about the use of normal.
I guess one more, are you seeing, or is this kind of a trending question, are any microplastics showing up in your water samples?
Yeah, excellent question. Thank you for that.
Thank you.
He wasn't an audience plant, I swear. Yeah, so at our branch, I'm kind of more on the groundwater side, but our surface water group has started this huge study in partnership with Health Canada to study microplastics. And it's a really tricky thing to study because almost every sampling instrument that you use will contribute microplastics to water. So it's really tricky to design a system out of all stainless steel components shipped in non-plastic packaging. So we have created these elaborate sampling rigs that are at the cutting edge, as far as we know, worldwide for sampling microplastics. So we're investing significant resources in them, and we've done a couple studies on like our deeper wells in like Deep Creek, Grizzly Valley. And just atmospheric deposition of microplastics is enough to contaminate groundwater wells with microplastics at a very low level, but they're detectable pretty much everywhere. It's a crazy phenomenon that we're starting to observe, and we'll move into kind of the results publication phase for those things. Steel casing wells even.
Don, after Louise's question, I have a question from online.
I'm from Eastern Ontario, and a lot of the, especially campgrounds, the water was very sulfonated. Is there a lot of sulfur in the water up here?
I thought you were gonna ask about sulfur in Eastern Ontario.
Well,
No, I'm just joking. My family's from there.
yeah. Well, I just know every time you went to go and get some water from the fountain, it was like, ew, and everything was yellow.
So yes, we do see sulfur in a lot of the water samples. The concentrations, it's usually we see sulfate. So it's sulfur with oxygen atoms. We see it distributed, pretty much, well, everywhere within the Greater Whitehorse area. The concentrations do vary, just like they do for the other parameters that Elliott was showing data for. And again, it comes down to a few factors, but the rock type is a major driver. And we do also, like uranium, see some elevated sulfate around historical mining areas. And sulfate is another one of the parameters that we can use to try and understand the movement of groundwater through those historic mining areas. So Elliott talked a lot about, excuse me, the uranium isotopes, which is a very unique way of looking at it and potentially a very powerful way. But sulfate is another one. And yes, we do see sulfate. Yeah.
I just want to kind of disambiguate sulfate and sulfide too.
Yes.
So there's different forms of sulfur. Sulfur is the atom, and there's different molecules that contain sulfur. So the sulfide is the one that you can smell. It smells like rotten eggs, right? So Matt was talking about sulfate, and sulfide. I mean, I'm sure many of you have encountered it. We're measuring sulfide. It's at very low levels, but it doesn't take a lot to actually smell it. The human nose is really good at detecting sulfide, and we don't have any trend data on sulfide, and the concentrations. There's no like health-based consideration around the sulfide that we are seeing. It's one of these aesthetic parameters that's as you know, it's not necessarily desirable in your water. One of the things I failed to mention in the presentation, but which we did mention yesterday, is that we've had conversations with hundreds of people at Whitehorse because we've gone to sample people's wells, and everyone is really keen to talk about their individual wells. And so we've heard a lot of observations, and a lot of people, and I'm sure some people in the audience will be familiar with this, have kind of been saying they're now getting more sulfide in the last couple of years. And I could speculate as to why that might be. We don't really have an answer, but we have heard that from several residents that they're sensing more sulfide in their well.
And going back to Eastern Ontario, so my wife's family's cottage is west of Ottawa, and they sometimes get sulfide in their drinking water. It's because they don't have their water heater turned up hot enough. So if you have your water heater temperature too low, microbes love that. And if you have sulfate in your water, the microbes will turn that sulfate into sulfide. So it's good, even though you might save a little bit of energy by operating your water heater at a lower temperature, it's best to go within the sort of recommended operating range because it will help prevent that sort of reaction.
Here's another question from online about noticing differences in well water. Person online here has noticed a very strong smell coming from the well water at the Deep Creek treatment facility, a chlorine smell, and is wondering what that smell would suggest the groundwater is being treated for and what issue that might be addressing.
So I can just kind of speculate on this, but my first guess would be a chlorine smell would be used to treat bacteria or microbial growth. So if there's a strong chlorine smell, they might have been doing just like a kind of chemical flush of the system as part of yearly maintenance or to address like a rising bacterial count. But without data from that system, it's hard to really say where the chlorine smell is coming from, but most likely would be from some kind of microbial treatment that they do as a course of regular maintenance.
Thank you.
Is that okay, Jane?
Yeah, so we're coming on 9:15. So I'm going to let there be about 3 more questions, and then we'll have to get out of this building. The staff at Beringia would like to go home.
Happy to stick around outside.
Excellent. Maybe in the parking lot. Go ahead, Don.
Okay, so my question is, I hope I've got this right, I may be incorrect here, but am I right or correct to infer from what you said that mining can contribute to increased levels of uranium and manganese water levels? And I'll tell you why I'm asking that question. Because right now there is a company exploring, drilling wells in the Whitehorse Copper Belt area. And I'm just wondering if they're successful in all their permitting and so on, if a mine ever exists again in that area, would it lead to a deterioration in the groundwater through the increased levels of manganese and uranium?
Yes, that's a great question. One of the things with the Whitehorse Copper mine site where we've been doing more monitoring is that all the wells there were installed after the mine was decommissioned. So there's no pre-mining information, right? So one of the important things for any modern mine is to get kind of pre-mining environmental information, including groundwater quality, so that they can detect changes over time. At the Whitehorse Copper site, we could never compare pre and post because there's no pre-data. One thing that's quite interesting with the uranium isotope data is that we think we have a tracer that distinguishes uranium that's associated with the weathering of the mine waste, and that would be different from the uranium that we're seeing that is from natural release from the rocks in the ground. So we do have a kind of a way to try and get a sense for whether or not there's been some additional release from weathering of mine waste. And the highest concentrations of uranium that we see across the study area, basically from Carcross cut up to the North Klondike Highway, are in groundwater right around that site, but they're quite localized around that site. Now, I can't speak to any future mine site. First of all, because any new project has its own regulatory process, and as part of that regulatory process, there's water quality objectives that are determined, there's treatment objectives that are determined. So what our study is able to do right now is identify among the rock types in the area which are the parameters that are more likely to be mobilized. We could perhaps make the assumption that some of the parameters that we see at the Whitehorse Copper sites are parameters that might show up elsewhere along the copper belt because the geology is similar. But any additional project would have to look at a detailed analysis of the rocks right in that area, and that's basically just like I've said about the private domestic well results. It's really hard to kind of take results from one area and apply them to another area. So any project has to have its own site-specific study, and that would be the same for any future mining project. So we're just kind of providing information that are things that might be good to keep in mind, but it doesn't mean necessarily that what's happening at one site is happening at another. And it also is worth keeping in mind that the Whitehorse copper mine was decommissioned in the 1980s, so a different regulatory environment than present day. And at that site, the Whitehorse copper mine, there's zero water management, water treatment whatsoever, right? And the uranium isotopes do seem to give us some hint into transport distance around that site, and it's quite localized. Again, for another project in another area, the groundwater flow paths will be unique to that area. The chemistry of the rock will be unique to that area. And so there'd be a whole bunch of work to figure out, what are the specific considerations for a specific other project.
But two questions, both are pretty quick, and I think the answers will be pretty quick. The first one is seasonality. Do you notice that the chemical composition of groundwater changes seasonally? If so, how much and what kind of things change? And the second one has to do with Whitehorse water supply. When I first came here, a significant proportion, if not most, of Whitehorse water was from surface water, was taken from Kwach'an Lake, and they changed that to my understanding exclusively wells. And it seems that surface water would actually be easier to manage because less mineralization. You wash your car, you don't get water spots. You water your plants, your soil doesn't become mineralized. But we've shifted away from that. I'm wondering if you have any insight as to why.
Seasonality. Great. I'll take the seasonality. Maybe Cole, you want to take the Whitehorse water supply? Okay, so seasonality, yeah, we can expect seasonal differences, and again, that's why if you test your well once, it's good to test it again at different times of the year. Jeff really showed kind of clearly how the water levels change over the seasons, and those changes can lead in changes in chemistry. I didn't speak to any seasonality in this project at all. We have, as it's a 3-year project, and over the course of that project, we have a few wells that we've been sampling at a higher frequency, so approximately quarterly. Yukon Observation Well Network, you guys also sample twice per year at most of your wells. We haven't worked out the seasonal data, but for example, in the AGWA project, we will, because we're going to look at, do we see any seasonal patterns? They might be predictable. You might see some parameters that increase or decrease in spring or winter or summer, or it might be a bit more random, and we don't know that just yet. Okay, so I'll pass it on to Cole to answer about the question about the switch from Kwach'an Lake to the Selkirk Aquifer.
Yeah, so I obviously wasn't around for that decision, but I can guess it's the rationale behind it is that surface water is just a lot more inherently vulnerable to contamination. So like we all know, if you've been on Kwach'an Lake, it's full of like pleasure craft up and downstream, like 7 lakes. Lots of people recreating in those areas. The risk of contamination for surface water is a lot higher. So the risk for a public supply system is that you're more exposed to contaminants that come in through surface water, and the riverbed sediments that underlie the Selkirk Aquifer system act as a really effective natural filter for water. So those silts and sands are very permeable, so the river water does interact strongly in those sandy areas. And as river water travels through those sands, it does a really effective job of filtering out a lot of contaminants. So the base kind of quality you get will be very similar to the Yukon River, but already through this gigantic natural filtering system that just kind of saves environmental health from a bunch of work and extra purification steps.
So a good example to illustrate that is Iqaluit, right? So Iqaluit takes their water from a river nearby, and there was this diesel tank that produced water and entered the river, and it really quickly goes right into the treatment system or the public supply system. So having that sand aquifer, the Selkirk Aquifer is a great aquifer. It's very productive, but it does provide a bit of a buffer to protect water from more rapid contamination and a lot more time for handling any possible changes to the water quality. And I think Brandon will know the answer to this. Brandon Mulligan or Cadia Rodriguez from the city. So the city will have specific answers on their water supply. But I think they also found it more cost effective actually to pull water from the Selkirk Aquifer because the treatment requirements were lower.
We live in Wolf Creek.
Sorry, I'm gonna follow up on your reference before. So in Whitehorse Copper, in the old Whitehorse Copper mine area, there's a lake essentially. So can I take from your earlier comment that there's not much spread or contamination from that lake? And I'm calling it contamination. I think it's just copper as far as I know, but there might be other things that are in that water that is in the pit that was the old mine.
Yeah, that's an excellent question. So you're talking about the pit lake, right? And we have sampled that pit lake. We've sampled surface water kind of throughout the site. In terms of transport, so that pit lake, we right now don't know where that water is going. It's a topic of active conversation with Stephanie here. We have maybe some ideas about where it's going. It's probably part of a groundwater flow system. And the next round of work that we'd like to do if we get more funding is to really understand the flow paths from that lake. It may be connected to other areas, but right now we don't know.
Thank you. It's helpful.
Yeah.
Yeah, we really appreciate the work you're doing. Thanks a lot to you and all your collaborators. It's really valued. We live in Wolf Creek, and the lot that we're on was one with a test well that would have been dug in the 70s. We've not been able to get the chemistry information from that testing and don't know if it exists. And we've been tested 3 or 4 times since then. On the figure that you showed, our lot didn't have a dot. So I don't know if that means your graph producers didn't put that dot on, but we'd be happy to share our results and to learn.
Yeah, it'd be good to be in touch. And if you want to get your well sampled, you can get in touch with us and we'll get you on our list. And if we've got capacity, we could collect a sample as well.
Yes, I wonder if you could just tell me what the condition of the aquifer under the city, like City of Whitehorse is now drawing water from these groundwater wells. And what is the condition of the health of the aquifer under the city?
Yeah, so we actually have an observation well in the Selkirk aquifer that we monitor. It's a tricky well because the aquifer is subject to pumping influence, and because it's very coarse grained, changes in water in like pumping levels will affect the groundwater level. But overall, we don't see any like long-term trend in aquifer storage because it is so connected to river levels. So if we see the Yukon River really start to drop, then levels in the aquifer will follow very shortly after that. So the level is mostly controlled by the river, and the water chemistry, I don't have the results in front of me, but I can say it's very good, healthy groundwater in the Selkirk aquifer. We're very fortunate here to have that as a resource.
I just wanted to ask, who do we contact, or how do we contact you if we want our well tested?
Shannon had cards printed out or something. Maybe just come talk to us at the end. So myself, Matt, Mary, Emily. So yeah, just come chat with us.
Well, that's a perfect segue for a plug. If you give Richard over there, Richard, can you he's going to be over at the membership table as we leave. And if you give Richard $10, he will, it's true, he will put you on our newsletter list. And I'm going to follow up with our newsletter group with some contact information and so forth for finding out more resources for if you want your well tested, what to do with the results, and just learning about generally water quality. So I'll follow up with that. I'll also put it on our Facebook page. But you don't have to give Richard $10. You can also go to our website and do it online there as well. We have a great sign up subscription, and we accept money online as well. But if you talk to Richard, maybe you can be convinced to bring better cookies. Then we also have, I have an appeal. We would love to be able to do these events on Facebook Live. But I've been told that our membership is too low. So everyone, if you can join our Facebook group tonight on your phone, That would help us get towards our goal of being able to do Facebook Live. Yes, there are 2 Facebook sites for Yukon Science Institute. Only one of them is currently working. If you have trouble finding the right one, get in touch with me through the website and I will send you the right one. But if you receive our newsletter after signing up with Richard, you'll also get Facebook links and we'll learn about all the upcoming talks and things like that, and CBC broadcasts and interviews that were held with the scientists tonight, and others will all be there as well. So please, follow up with us and join our group. It would be super. I think that there's probably one more question over on this side, Dawn. I know folks had their hands up for a bit. And then, Richard and one more, and then we'll head home.
Just one question for in behalf of the well water owners. I imagine there's difference in the water flow, the seasonal difference in the water quantity in the well water, and would it be a good idea to test twice, like once in the summer and once in the winter time?
Absolutely. I mean, more seasonal information is good. In terms of what we're trying to achieve in our current project, we're really trying to get spatial coverage. So we have 3 years of funding. We're trying to get as many samples across this area as possible. There's a few wells where we're able to sample at a higher frequency. But for your own interest, it is good to get seasonal information because it could be important.
Thank you very much.
Oh, go on, it's okay. Ask your question.
Nobody's mentioned hot springs, and I'm really curious to know what's going on around that particular region. But maybe when you come back,
I would love to sample them and tell you. Anybody can get me access. I've been working with a colleague. We've been sampling hot springs all up and down Western Canada, and we don't have one from Tahiti.
So we have the boreholes near there or the water wells near there showing elevated temperatures. An idea of what's going on.
Anybody knows how to get me or the team access, I would be. Yeah, raw water, just raw water. That's it. Yeah. Thank you.
Excellent. Well, I'll be sending out some information about groundwater that Cole is going to forward to me afterwards. And
I just want to interrupt for a brief moment just to thank everyone for their attention, but particularly people who allowed us to sample their wells. Really, we've learned so much about groundwater Whitehorse, and it's thanks to the community here. So thank you.